All right, I'm going to go over exam 2 now. So let's see. Problem 1, graphs of rational functions. So we're given a graph and asked to find all the things about it. So first off, the y-intercept. That's just where it crosses the y-axis. The intercepts are always points. So that's the point 0, 1. Looks like 0, 1. The x-intercepts. So there can be more than one x-intercept, but there can only be one y-intercept. The x-intercepts where it touches the x-axis, these are also points. So we have -1, 0, and 2, 0. The vertical asymptotes, let's see, those are where it jumps. Looks like there's one right here and one right here. So those are the vertical lines x equals -2 and x equals 1. The horizontal asymptote are where the end behavior goes towards. So it looks like we're over here at the line y equals 1. Okay, now we want to find a formula for this function in factored form. So we already have all the information that we need. Remember, the x-intercepts basically go in the numerator, the vertical asymptotes go in the denominator. So let's make sure we don't have to do any additional work for this one. Oops. Y equals, let's see, I'm going to put an A here. Oops. And A here, just in case we need to do some scaling. And the x-intercept -1, 0 goes to x plus 1. The other one is x minus 2. And the vertical asymptotes are, okay, x looks like plus 2 and x minus 1. Those are from the vertical asymptotes. So we want to make sure that the y-intercept is 0 and that the horizontal asymptote is y equals 1. So the horizontal asymptote, we just look at the x values or the multiplicity a lot of time as well. Since there's an x squared in the numerator and an x squared in the denominator, and they both basically cancel out, leaving us with 1. That means that a should also be 1. The other way of doing it is by looking at the y-intercept, which is 0, 1. That means if we plug in 0 for x, we should get 1 out. So if we do f of 0 equals a 1 times -2 divided by 2 times -1, which these all cancel out to be a, which we want to be 1. So that tells us that a equals 1, and we can just kind of ignore it. So here, our function is f of x equals x plus 1, x minus 2 over x plus 2, x minus 1. There we go for problem 1. Problem 2, graphs of rational functions. So now we're given a rational function and we want to graph it. So we want to find the y-intercept. Remember, that's when we plug in 0 for x, that's -2 over -2 times 1, which just equals, the -2's cancel out, which just equals 1. So y-intercept is 0, 1. The x-intercepts are, we set it equal to 0 and solve. In this case, we have x minus 2 over x minus 2, x plus 1 equals 0. Now, a lot of us are going to be tempted to just look at the numerator here and say that the x-intercept is the point 2, 0. But notice that we also have the same fact right here. So these will actually cancel each other off. So if we actually do that right up here, these will cancel each other off, leading to f of x being 1 over x plus 1, where x cannot equal to 2. So in this case, there are actually no x-intercepts, does not exist. Then the vertical asymptote we're going to use just what's in the denominator left over. So that's going to be the line x equals -1. Now, if we didn't cancel the x minus 2 in the numerator and denominator off before, then at this step we would see that there's an x-intercept at x equals at 2, 0, and a vertical asymptote at x equals 2. We can't have an intercept and an asymptote at the same place, so that's how we would, be clued in to go back and change that and say that, oh, there's actually a hole there. So the horizontal asymptote, since now in a simplified version, we have 1 over x plus 1. As x gets really big, then the 1 over x goes to 0. And also just remember that since there's more powers of x in the denominator than the numerator, it'll go to 0. And the coordinates of the hole, let's see, that's where we plug in x equals 2 into the simplified function to find out where the hole actually is. So let's see, at f of 2 equals 1 over 2 plus 1 equals 1/3. So here our coordinates are 2 and 1/3. Now to graph it, we just gotta put everything on the graph for now. So y-intercept is 0, 1. There is a hole at 2, 1/3. Let's see, there's a vertical asymptote at x equals -1. There's a horizontal asymptote, y equals 0. And let's see, here we can do a sine line using the 1 over x plus 1. So our sine line just changes at x equals -1. So if x is greater than -1, then we're positive. If x is less than -1, we're negative. So now we just connect the dots, which makes sense based on what we already have drawn on the graph. So connecting the dots, we know we're positive on the right hand side of the vertical asymptote. So we're going to hit the intercept. We would be going through the hole, but it's a hole, so we're going to skip it. We're going to go like this, put our arrows on. Then it's negative on the left hand side of the asymptote. So now we're just going to draw this curve right here. So that is the graph of this function, remembering the hole there. Then problem 3, rational inequalities. So we want to solve the inequality 3x plus 1 over x minus 1 being greater than or equal to 2. Writing it in interval notation. So we can, there's a graph here in case we want to graph it, but it's not required, so I'm going to skip that part. A lot of people, when they see a problem like this, they're tempted to multiply both sides by the denominator, but because there is an inequality sign there, that actually loses information. So we can't do that. We want to make sure and keep all the information with us. So what I'm going to do first is I'm going to subtract the 2 from both sides. So we get 3x plus 1 over x minus 1 minus 2 being greater than or equal to 0. And now on the left hand side, I want to subtract these two things, so I need to have a same common denominator. So I'm going to multiply the -2 by x minus 1 over x minus 1. So 3x plus 1 over x minus 1 minus 2 times x minus 1 over x minus 1. That is 3x plus 1 minus 2x plus 2, because we need to remember to distribute the negative sign as well as the 2, over x minus 1. Simplifying that, we get, let's see, x plus 3 over x minus 1 is greater than or equal to 0. So now we have it all simplified into one fraction, and it's greater than or equal to 0 on the right-hand side. Now we can just do a sign line to figure out when this is true. So our sign line, do it over here. I'm going to put what makes the numerator 0 and what makes the denominator 0. So the numerator is 0 at x equals negative 3. The denominator is 0 at x equals 1. Now I'm just going to fill in the sign line. So if x is greater than 1, say if x is 2, 3, or even 100, well, 100 plus 3 is positive, and 100 minus 1 is also positive. So positive divided by a positive is positive. And then the multiplicities of these are both 1. So they're both odd multiplicities, which means it's going to switch signs as we jump across. So now we have our sign line. After all that, we still have this greater than or equal to sign here, which means we want to know the values of x that make this positive. So that's going to be this portion and this portion. So negative infinity to negative 3, unioned with 1 to infinity. And because it's less than or greater than or equal to, we have to know which endpoint we can include. So let's see. If x equals negative 3, then that's in the numerator. It makes the numerator 0, which is fine. 0 divided by something is still 0. But if x equals positive 1, then the denominator is 0, and we're dividing by 0, which we can't do. So we're not going to include that point. So negative infinity to negative 3 inclusive, unioned with 1, not including 1, to infinity. Okay, roots of polynomials. Given that x equals 3 is a root, we want to find all real and complex roots. So we're going to use synthetic division here with x equals 3. So let's see. Remember with synthetic division, we're just going to pull out all of the coefficients and not use the x's at all. So I'm going to say 3, and then the coefficients are 2, negative 6, 8, negative 24. Okay, the first number gets dropped down, so there's a 2 there. 3 times 2 equals 6. Negative 6 plus 6 is 0. 3 times 0 is 0. 8 plus 0 is 8. 3 times 8 is 24. Negative 24 plus 24 is 0. So we always want to get a 0 here. That means we've done it right. So what this means is that if we factor out the root at x equals 3, we get x squared plus, that's 2x squared plus 8. Now we want to factor this thing out as well. So to factor out 2x squared plus 8, first off I'm going to pull out the 2. So that's x squared plus 4. And then x squared plus 4, if we set that equal to 0, so I'm just going to go up here, x squared plus 4 equals 0, gives us x squared equals negative 4. And now we take the square root of both sides. So the square root of a negative number is imaginary. So we have plus or minus 2i. So now our roots are x equals 3, 2i, and negative 2i. So now we need to, for part B, write in completely factored form. So factor form, there's an x minus 3, x minus 2i, and x plus 2i. But here we forgot about something. At some point in the last problem, we factored out a 2. We can also see that in the original problem up here, where there's a 2 in front. So if we just left the answer like we have it, we would be wrong because we wouldn't have that scaling factor. So we need to make sure and keep that there. So make sure and add that as well. Easy to forget about. Okay. So then for problem 5, roots of polynomials, it's a very similar question. Using the fact that x equals 1 and x equals 2 are roots, we want to find all real and complex roots. So we're going to do the same thing that we did last problem and use synthetic division. So 1, 1, 2, -7, -8, and 12, just pulling out the coefficients of the problem. First number drops down to 1. 1 times 1 is 1. Plus 2 is 3. So times 1 is 3. Minus 7 is -4. Times 1 is -4. Plus -8 is -12. Times 1 is -12. -12 plus 12 is 0. We like getting the 0. So this tells us that once we factor out the x equals 1, or the x minus 1 factor, we get x squared plus, there's 1, 0, x cubed plus 3x squared minus 4x minus 12. And now I'm just going to actually tack this on right here. I'm going to use synthetic division to factor out the x equals 2. So I'm just going to put a 2 right here and do this again. So the 1 drops down. 2 times 1 plus 3 is 5, times 2 is 10, minus 4 is 6, times 2 is 12. Gives us 0 again. So here we have x squared plus 5x plus 6, which we can actually factor ourselves. We could use the quadratic formula, but here we're going to factor in instead. So two things that multiply to get 6 and they add to get 5. Well, it's 2 and 3. So now our roots are x equals 1, 2, I'm going to say 2 again, and 3. If it's just asking for the roots, you don't have to write 2 twice, but it's helpful to see it there twice, especially if we're going to, for the next step, we're going to write it in factored form. We want to make sure we retain that multiplicity. We could have also written x equals 1, 2 with multiplicity of 2, and 3. So to write in factored form, we just have x minus 1, x minus 2 squared, and looks like I actually made a mistake there. So this is the factored form. This gives us the roots, x equals -2 and -3. So let's erase these really fast, and these ones. So there's 1, 2 that were given initially, and then we have -2 and -3. Forgot about my negative sign. Don't worry, forgetting about negative signs never goes away. Okay, now we can put these in factored form. So there's x minus 1, x minus 2, x plus 2, and x plus 3. There we go. Let's see. Now, problem 6, writing functions from roots. So here we're given that the polynomial p of x has degree 3, roots x equals 2 and x equals 3i, and a y-intercept at 0, -36. So we want to find a formula for this. So if we have the roots x equals 2 and x equals 3i, Remember, imaginary or complex numbers, when they're roots, they always come in complex pairs. So if x equals 3i is a root, then x equals negative 3i is also a root. And that gives us our degree of 3. We have 3 roots, 3 degrees. There we go. Now we just need to worry about the x-intercept, the y-intercept, being at the point 0, negative 36. So I'm going to write down my guess for p of x. I'm going to include the a, because that's going to be how I change my vertical scaling. And x minus 2, x minus 3i, x plus 3i. So that's our initial guess. Now we want to plug in 0 for this and figure out what a needs to be to make that equal to negative 36. So p of 0 equals a, negative 2, negative 3i, 3i equals negative 2a, and negative 3i times 3i is negative 9i squared. And remember, I squared is negative 1. So that's negative 2a times 9, or negative 18a, which we want to equal to negative 36. Well, solving for a, we get just a equals 2 by dividing 18 by a from both sides. Now we're just going to plug that 2 into our a up here. So now we have p of x equals 2 times x minus 2, x minus 3i, x plus 3i, and that's our equation. Okay, problem 7, we're solving logarithms. So log base 2 of 1/4. So there are 2 main ways for this one. We could set this equal to x and then convert it to exponential form. So log base 2 of 1/4 equals x. That's the same thing as saying 2 to the x equals 1/4. And then, so 2 to what power equals 1/4? Well, 2 to the negative 2 equals 1/4. Another way we could do it is we could do log base 2 of 1/4, and if we make 1/4 to be 2 to the power of something, we can simplify it. So 1/4 is 2 to the negative 2. Then we can use the exponent rule to bring this out front. Oops. There we go. So let's see, equals negative 2 log base 2 of 2. And log base, so any log that's argument is the same as the base is just 1. So those cancel off, leaving negative 2. So just 2 different ways of thinking about it gets us to the same answer. For part B, log base 6 of negative 36, well, we can't have a negative in any logarithm, so whenever we see a negative in there, I'm just going to say it does not exist. Part C, log base 7 of 1. Well, if we do what we did in the first problem, log base 7, oops, looks almost like a 7. Base 7 of 1 equals x. Then 7 to the x equals 1. Well, anything to the 0th power is going to equal 1. So whenever we see a 1 in a logarithm, doesn't matter what the base of the logarithm is. If a log of any base of 1 is always going to be equal to 0. Then for part 4, I'm going to do it the same way. Log base 16 of 8 equals x. Gives me 16 to the x equals 8. And now I want both sides, the bases, to be a number of the same base. So 16 is, let's see, 2, 4, 8, 16. 16 is 2 to the 4th. So that's the same thing as saying 2 to the 4th to the x equals 2 to the 3rd. And if we have an exponent to an exponent, then we just multiply the exponents. So that's the same thing as saying 2 to the 4x equals 2 to the 3rd. And now, since they're the same bases, the exponents have to equal each other. So this tells us that 4x equals 3, and then x equals 3/4. So this logarithm simplifies to 3/4. Okay, and then for the last part of this problem, log base 9 of 3. I'm just going to keep it in this form. Log base 9, but 3 in terms of 9 is just 9 to the 1/2. The square root of 9 is 3, so we didn't change anything. Now we use the exponent rule to bring the 1/2 out front. 1/2 log base 9 of 9, which this cancels off, leaving just 1/2. So there we go for all parts of problem 7. And problem 8 is the last one. So we're doing complex arithmetic. Z equals 1 minus 2i, w equals 2 plus 3i. We're just going to add, subtract, multiply, divide. So z plus w is going to be, let's see, 1 minus 2i plus 2 plus 3i. So we're just going to combine like terms. So that's 1 plus 2 plus negative 2i plus 3i, or 3 plus I. For part 2, z minus w, we're going to subtract them. So 1 minus 2i minus 2 plus 3i. Remember, we have to distribute the negative here. So 1 minus 2i minus 2 minus 3i. And here we just combine like terms. So 1 minus 2 is negative 1. Negative 2i minus 3i is negative 5i. Okay, z times w. So that's 1 minus 2i times 2 plus 3i. Now we're just going to FOIL it. So let's see, write it down here actually. So first 2 plus 3i minus 4i minus 6i squared. So let's see, 3i minus 4i is minus I, and then I squared equals negative 1. So that's minus 6 times negative 1, so it's actually plus 6, which equals 8 minus I. Okay, and then the conjugate. Remember, a conjugate is just when we're taking the opposite side of the opposite sign of the imaginary part. So if w is 2 plus 3i, w conjugate is 2 minus 3i. Okay, then for z divided by w, I'll write down first 1 minus 2i divided by 2 plus 3i. We don't like having the imaginary portion in the denominator because we can't write it in the form of a plus bi that way. So we're going to multiply by the conjugate of the denominator. So we're going to multiply by 2 minus 3i over 2 minus 3i. So it doesn't change the value, since we're effectively multiplying by 1, it just changes what it looks like. So here we can multiply the top together, so that's, let's see, 2 minus 3i minus 4i plus 6i squared over 4 minus 6i plus 6i and minus 9i squared. So here we go. Numerator is 2 minus 7i minus 6 over, let's see here, negative 6i and 6i cancel off, 4 plus 9. So this gives us negative 4 minus 7i over 15. So we can leave it like this. We could also write it as negative 4 over 15 minus 7 over 15i. That way it's in the form of a plus bi. And then just write that in a little box here. Negative 4/15 minus 7/15i. Alright, and that is exam 2.